All right, so let's look at a problem here. Females have pulse rates that are normally distributed with a mean of 74 and a standard deviation of 12.5. If we select one adult female randomly, find the probability that her pulse is less than 80. The first thing to recognize is that we are selecting one person randomly and finding a probability of getting a certain result. That is 6.2, okay? And we've done this, but we need to do this. We need to do a 6.2 version of the problem and then right next to a 6.4 so that you can know when to use which approach. All right. So the way this is going to work is we know that pulse rates are distributed normally. So we're going to have our normal curve. We'll have a mean of 74. We'll have a standard deviation of 12.5. All right. And we want to know what's the probability that this person has a probability that's less than 80. So we're going to have our critical value at 80, and we want to be less than 80. And so that puts us right here. We want this area. That's the probability that we get that particular result. Right? So we know how to do this. We come in and we say we need to first find the z-score of our critical value. So 80 minus 74 divided by 12.5, right? Just using our regular formula, gives us a z-score of 0.48. And if we look up in our table, 0.48 in the positive z-scores table, we should get 0.6844. So what that means is this area is 0.6844. So there's basically, so the probability that the value of x is less than 80 is, or the probability is 0.6844 or 68.44%, right? So there's a pretty good chance that if we choose one at random, they'll have a blood pressure or a pulse less than 80. Okay, so now we're going to do one that comes from 6.4. And in 6.4, what we're doing is we're not choosing one person at random, but in this case, we are choosing 16 at random, 16 females. And the question is, what's the probability that their average will be less than 80, right? So it's the same thing. In order to find these probabilities, we're going to be turning to our normal curve, right? And so our normal curve, in this case, it's the distribution of the means, because this is a question about means. So the mean of the means, right, is just the mean of the population, which was 74. That doesn't change. That's real handy. Those means are the same, right? But the standard deviation of the means, or the standard error, is the standard deviation of the population divided by square root of n. So in this case, it'd be 12.5 divided by square root of 16, right? 12.5 divided by 4, which is square root of 16, 3.125, all right? So that's going to be the standard deviation for that distribution. Once we're there, then we proceed the same way. We say, okay, our cutoff point is up here at 80. And we want the probability of being less than that. So again, we want this probability. So in order to find probabilities under normal curves, we need to find the z-score of our critical point, of our boundary. So 74 minus, sorry, not 74. Let's try that again. So it's going to be, our boundary is 80. I need to label that down here. 80 is our boundary. So we're going to have 80 minus 74 divided by this standard error. And that's going to give us the z-score of this critical value. So I'm getting 1.92. Okay, so that's the value I'm going to look up in my table, in the positive z-scores table. 1.92, and that gives me 0.9726. So 0.9726, that's the area that I want. So the probability of being less than 80, of having an average less than 80, is 0.9726, 97%. So there's a lot higher probability that the average is less than 80 than a single scores at less than 80. Why? Because averages tend to clump around the center. They'll be much more likely to be here. So it's much more likely, since our shaded area covers that middle section, that's why the probability is greater. There's less variability. So those are your two problems that you want to consider and just compare next to each other. In one case, you're just selecting one person or one individual. In the other one, you're picking 6 and asking about their average. That's the big difference between these. So here's a question. Why can the normal distribution be used right here in this part, in part B, even though the sample size does not exceed 30, right? Our sample size is 16. So why can we assume normality? Well, remember, you can assume normality in two cases. Either if your sample size is above 30, 30 or greater, or if the original population is normal. And the original population is normal. The population of female blood pulse rates is normally distributed. So that's why we can assume normality for the sampling distribution.